Welcome to the 45th lecture on computational mathematics with SageMath. In this lecture, we shall look at finding numerical roots of algebraic and transcendental equations. So henceforth, we shall look at some numerical methods in SageMath. So let us get started. So numerical analysis concepts in SageMath can be explored using basically three packages: NumPy, SciPy and CVOPT. We have already seen NumPy and SciPy. NumPy is an excellent package in Python that has facilities of fast array computation. It also includes linear algebra package, vectorized math routines and random number generators. It has programming styles very similar to MATLAB. On the other hand, SciPy builds on NumPy and provides many different packages for optimization, root finding, statistics, linear algebra, fast Fourier transforms, etc. CVXOPT is an optimization package which can solve linear and quadratic programming problems, and it also has nice linear algebra interface. Of course, you can write your own programs in SageMath in order to solve problems in numerical analysis, and we will be doing for some of the methods. So we shall look at finding roots of algebraic and transcendental equations in one variable, namely fx equal to 0. So when I say algebraic equation, basically it means that fx is a polynomial. Transcendental equation on the other hand will be combination of polynomials, exponential functions, algebraic trigonometrical functions, etc. So let us start with a problem. We want to find a root of minus 2x cube plus 2 sin x square plus e to the power x minus 5 equal to 0. We want to find x for which this left hand side is equal to 0. So before we find a root, let us plot graph of this function. So first let us declare this function. When we, after declaring this function, let us plot its graph between, let us say, minus 3 and 3, and figure size is equal to 4. So this is what we see. So we can see that between minus 3 and 3 it has a root. Actually the root lies between minus 1 and 0. So we want to locate that root. We have already seen this in SageMath. So one can try to use solve function. So when I say solve fx equal to 0 for x, it may or may not give a solution. So for example, in this case it is not finding a solution, it is unable to find x explicitly. So this may not work. So in that case we have seen that we can use what is called f dot find underscore root. So let us look at what is find underscore root. It is an inbuilt method in SageMath. So let us first take help on this. So f dot find underscore root double question mark, which will give you detailed document. So this says that find underscore root of self, that is the function, and a and b are the interval, the end point of the interval. You need to mention the variable with respect to which you want to find a root. You have to also give the tolerance limit and the number of iterates, maximum number of iterates. By default it takes 10 iterates, and you can mention the output true or false, that is a Boolean option. And what is it? So it finds numerically a root of a function f in a closed interval ab or BA. So it does not matter, you can give A, B, where A could be less than B or A could be bigger than B, and if possible where the cell function has one variable is of one variable. So basically this works with only one variable. If you have multivariate function and then you want to find roots, this does not work, right. And also here it will find solution only when there is a root between A and B. So you can go through this document and see there are several examples. It also tells you how this function is defined. So basically if you look at this, actually uses a function find root which is defined inside SageMath numerical optimized package. So if I try to take help on this package, then let us see what we are going to get. So let us import sage.numerical.op, right. Once we have imported this, then let us see what we will get. If I say sage.numerical.optimize dot and then tab. So you can see here this this has many functions. One of them is find fit, which again we have made use of when we wanted to find or fit base fit line or parabola, etc. Find underscore local maximum, find local minimum. This also we have seen in calculus. It can also solve linear programs, that is linear programming problem, and it can find minimizer and similarly constraint minimization function also, right. So this is inside optimize, numerical optimize, you have several methods. One of them is find root. So this is what basically Sage uses in order to find root of a one variable equation fx equal to 0 or 0 of fx, right. So let us look at how we can find a root. We already saw that this function fx has a root between -1 and 0. So if we try to give this f dot find underscore root -2 comma 0, this tells me that the root lies at -0.8842089 and so on. That is the point at which fx equal to 0, right. In case we want to find a root between 0 and 1, if I say if I give the interval 0 and 1, then we already know from the plot that this does not have a root, and therefore it will give you an error. This is an error, it says runtime error, and at the end it tells you that f appears to have no 0 on this interval. So in case you are providing an interval which does not contain a root using find root function, then it will throw an error, right. You can also give an option called full output equal to true. In that case, what does it say? It gives you root along with option converged, and it says that converge equal to true. So numerical methods, when you apply any numerical methods, it may or may not converge. There are certain criteria when a sequence of iterate converges to a solution. So in case it has not converged, it will give you the answer false, and then it also tells you that how many times the function has been called. In this case 10 times function were called, and the number of iterations which is required is 9, and the root lies at this. If I increase the tolerance limit, so for example if I say tolerance, I think it was called xtol is equal to, let us say 10 to the power let us say 1 e minus 12, then it again it requires only 10 calls, right. So let us look at how we x tolerance, it is already 10 to power 13. So, it does not 10 to power 10 is beyond that. So, if I say 10 to power 20, it may require more number of iterations. No, it requires only this. So, it is in this case the convergence is quite fast. Whatever method it is using, it converges quite quickly, right. So, this is what you can use, namely find underscore fit to a given function in order to find a root of this function. So, Sage provides you very nice way of plotting the graph. So, first you can plot graph of the function and locate the interval in which it has a root and then apply find underscore fit, right. That is how you can find root of an algebraic and transcendental equations. As I said, you can write your own program. You can write Python program and run in this Sage worksheet. So, for example, let us look at, suppose we want to develop our own program in order to find a root of this function using bisection method. So, bisection method is very simple, and I am sure all of you would have studied this bisection method. So, let me just show you. This is a user defined function for bisection methods which requires input f, the interval a and b, and the tolerance is 10 to the power minus 5. You can increase this tolerance to 10 to the power whatever, 10 to the power, let us say I will say 10 to the power minus 10, and a and b are made float, because in case you give this integer, then most often you may end up rational number as output, which may look somewhat ugly. And then you also convert this tolerance to float, define initial interval as AB. So, this will give you a tuple of intervals, and then the number of iterations which is required in order to find a root in an interval of length, let us say tolerance limit, in this case 10 to the power minus 10, that is given by n is equal to integer part of log of absolute value of b minus a divided by the tolerance limit divided by log of 2, right. So, and then start with iteration 0 and then find the value of a plus b by 2, that is midpoint, check value of f at a, f at b and f at c. In case f at a and f at c product is less than 0, that means root lies between a and c. So, you redefine AB as AC, and otherwise you redefine this as CB. Of course, you could also check if if C is a root, that is if FC is equal to 0 or value of FC is less than the tolerance limit, then you can stop here itself, you can use break, or otherwise you keep on appending this interval AB in the interval AB and then increment the iteration by 1, and then at the end you return the midpoint and also the set of the intervals. Okay. So, this is, you can of course modify this, include more options here. For example, you can check whether A is less than B or not. You can also check whether AB contains a root. All these things can be included here, right. Now, let us call this function bisection method for the same function fx which we chose earlier. So, this is, now let us see what is the value of c. C is this, and if I look at what is the interval that intervals is what I have given, then these are the interval. This is the first interval, then this becomes this, that, and so on. So, that is how it is approaching, right. So, in this case let me instead of minus 3 to 3, let me give you minus 3 to minus 3 to 0, and this is what you get. So, you can see here there are so many iterations which is required in this case, and one can even try to plot all these intervals, bisecting intervals containing a root, just to visualize how this iteration proceeds. So you can see here the initial interval is -3 to -1, and then this is a root, and this is the first interval, this is the second interval, third interval, fourth, and so on. You can see here the length of the interval is becoming very small, right. Next, let us write our own program for secant method. The secant method, this iteration scheme is given by xk plus 1 is equal to xk minus f at xk into xk minus 1 divided by f of xk minus f of xk minus 1. Again this I am sure you must have seen this. So let us write a program for this secant method. Again very similar inputs we are giving. Maximum number of iteration is 200, tolerance limit is 10 to the power 7. You can increase this to 10 to the power 12, and then let us execute this. In case you find that the number of iterate is equal to the maximum IT and still you have not obtained this within the tolerance limit, you can print a message saying that the convergent is not achieved, and that is same as what you saw flag in case of inbuilt function find underscore root. Now let us run this and call this function for fx. This is again the root is minus 1.30 and so on. Okay. Similarly, you can write your own program for Newton's method. The iteration scheme in Newton's method is given by xk plus 1 is equal to xk minus f of xk divided by f dash at xk, and you can create user defined function for this. It is fairly simple, very simple program. This we did in Python also, and this you can see here, this is exactly a Python program. It is nothing to do with Sage. We are not using any Sage functionality here. We are using Sage functionality only for plotting and visualization, right. So and then if we run this, call this Newton's method, in this case you need to input f and df, that is derivative, right. Of course without this also you can make use of now Sage functionality and find the derivative, define this df as f dot dif and then run this, and in this case you can see here we have passed df as f dot diff, and the initial guess is minus 2.5. If I give initial guess, let us say 2.5, then also it is able to find. So this is working. If I give you, let us say 12.5, then also it is able to find. In case if I give minus 12.5, then also it is able to find. So this function is quite nice. It seems that whatever initial guess you give, then it is able to find a root. So let us say for example if I give minus 102.5, then also it is able to find. Okay. So this because it is looking at 200 iterates. Okay, fine. So what it means is that you can write your own programs for all these methods. There are several other methods to find a root of a quadratic root of a algebraic and transcendental equations. So either you can use find root or you can create your own user defined functions, right. So let me leave you with a few simple exercises. So try to solve these equations, find roots of these equations using secant method, this one using Newton's method, and this also using Newton's method, and in each of these case you can verify this using inbuilt function find underscore root. Of course you should also plot graph and then try to see the interval in which it has a root. Okay. So next time we will look at how to solve a set of or system of linear equations numerically.